Let's think about measuring voltages. I have here a solution of copper sulfate and some copper metal, a copper electrode, solution of zinc sulfate and a zinc electrode, and I've got a voltmeter. So we'll put the copper into the copper solution, the zinc into the zinc solution, hook up the electrodes, and see if we can measure a potential. So let's go ahead and start our experiment. We'll open up the copper sulfate jar, nice blue solution in there. Zinc sulfate is a colorless solution. We'll put the piece of copper into the copper 2+ solution, put the piece of zinc into the zinc 2+ solution, and we'll take our leads from the voltmeter. By the way, the voltmeter is sitting on a purple piece of paper simply to make it a little easier to see the white numbers and the black needle, hard to see on the black bench, right now pointing towards 0 volts. So let's see what we can do. Let's hook up one lead to the copper and another lead to the zinc and watch the needle, and nothing happens. Oh, well, that's actually because we don't have a complete circuit yet. Even though we have the 2 electrodes hooked through the voltmeter, we don't have the 2 solutions in electrical contact. So what we're going to do is use what's called a salt bridge. Now what we've got here is a jar of sodium chloride solution and some pieces of paper in this. Let's see if we can fish out one piece of paper. There's one. So what I'm going to do is put one end of this piece of paper into the copper sulfate solution, and when we put the other end into the zinc sulfate solution, we'll watch the voltmeter, and there it goes. It just jumped to a negative voltage over to the left away from 0. I wonder why it went negative. And I wonder what would happen if I actually switched the 2 leads to the voltmeter. Let's try that. So as soon as I unhook one of them, it goes back to 0 volts. What if I put the black one on the zinc now, and the red one on the copper? Let's watch the voltmeter, and there it jumps positive. Went away from 0 over to the right. So this is how one can actually measure voltages of one half reaction versus another. In the experiment we just watched, it's worth noting that in the electrochemical cell, the 2 half reactions were separated in space. This is different than the experiment we saw in the previous module, where we put pieces of zinc directly into a flask with acid. There, we were mixing 2 reactants. Here we have 4 chemical species, 2 metals and 2 solutions containing metal ions. Of those 4, 2 will be reactants and 2 will be products, but all 4 are present at the start. The reaction did not go until the 2 half reactions were connected with a wire, which in this case went through the voltmeter, and a salt bridge. With a voltmeter in the circuit, we are measuring the potential of one half reaction versus the other. If you use a voltmeter for this purpose, you need to pay attention to how the leads are connected, as one lead is considered the reference half reaction, and the potential of the other half reaction is measured versus the reference. If you look at potentials in our table of half reactions, the hydrogen half reaction is considered the reference and is set at 0.00 volts. This is actually a difficult reaction to handle experimentally, since you need 1 molar acid and 1 atmosphere pressure of hydrogen gas above the solution, so in practical terms, it's not used very often. But all the potentials in the table are relative to it. If instead of a voltmeter you place a load in the circuit, then we would call the system a battery, and we can extract work from that battery. In the demonstration with the voltmeter, we started with 4 components, 2 metal electrodes and 2 different metal ions in solution. Electrons spontaneously flowed toward the half reaction of more positive potential. This is called a galvanic cell, where the electrons move spontaneously. There is some other terminology that we need to pay attention to. we define the cathode as the electrode where reduction takes place. The anode is then the electrode where the oxidation takes place. One way to remember that is with a small and a large animal, a red cat and an ox. Reduction takes place at the cathode, and the anode has oxidation. Let's take a look at an image from our textbook of a galvanic cell with copper on one side and iron on the other. The two metal electrodes are dipped into solutions of their 2+ cations. They are also connected by a wire through a voltmeter. The way the electrodes are hooked up, the voltmeter expects the half reaction on the left to be more positive, and that is confirmed by the positive voltage measured. In this cell, effectively, iron is the reference, and the meter is measuring the copper potential versus the iron. Electrons go through the external circuit, the wire, and the voltmeter toward the more positive potential, as you would expect a negatively charged electron to do. Notice that the iron half reaction is labeled as the anode. Electrons are leaving the iron half reaction. Electrons being lost is an oxidation, which is defined as happening at the anode. You'll notice the iron half reaction is written as an oxidation, with iron losing 2 electrons to form iron 2+ ion. The copper reaction is labeled as the cathode. Electrons are going into the copper half reaction. Gaining electrons is a reduction, which is defined as happening at the cathode. You'll notice the copper half reaction is written as a reduction, with copper 2+ adding 2 electrons to form copper metal. Let's put this picture in motion. Here in our animation we have the setup with a solution of copper 2+, shown by the blue color in the left-hand beaker, and a copper electrode. On the right-hand side we have a beaker of iron 2+ ions and an iron electrode. The two solutions are connected by a salt bridge, and there's a voltmeter at the top, but notice it's not hooked up to iron yet. So let's go ahead and hook up that electron and see what's happening. When we do, notice coming out of the iron electrode up into the voltmeter are electrons. They're shown 2 at a time. They go through the voltmeter and over into the copper electrode. So the copper side is gaining electrons. Gaining electrons is a reduction, and you see the half reaction underneath the copper beaker written as a reduction. You may see the blue color of the solution getting dimmer and the copper electrode actually getting larger in this animation. Now, since the copper solution is losing copper 2+ ions, the function of the salt bridge is to replace those charges, simply for charge balance, and 2 potassium ions come out of the salt bridge into the solution for every copper 2+ ion that's lost. So a reduction is defined as what occurs at the cathode. The copper in this case is the cathode. Let's move over to the anode. We'll replay this animation and look at what happens on the iron side. Again, the iron electrode is losing 2 electrons. Because it's losing 2 electrons, we have iron atoms shown at the surface converting into iron 2+ ions and floating into solution. Notice that this is an oxidation, losing electrons, and the half reaction written underneath the iron beaker is written as an oxidation. You may see the iron electrode actually getting smaller in the animation, losing iron metal going to iron ions which float away. Because iron 2+ ions are being added to the solution, 2 negative ions, chloride in this case, come out of the salt bridge simply to neutralize the charge. Electrons go through the wire on the top. The salt bridge is simply there for charge balance.